Vector basics. Let's look at a generic vector A. This vector will be in R3, meaning three-dimensional space. The components A1, A2, and A3. This vector could also be written as A1 times unit vector I, often with a hat, plus A2 times unit vector J, plus A3 times unit vector K. Just as a review, unit vector I with the hat is the vector 1, 0, 0. Unit vector J is 0, 1, 0. And finally, unit vector K is 0, 0, 1. If we now look at the magnitude of this vector, we indicate the magnitude with these two bars around it, then it's going to be like the three-dimensional version of the distance formula, where each of these components is squared. So it's the square root of the components squared. So now another important property is if we take the magnitude and we square it, then we simply get the sum of the squared components, as shown here. That becomes an important property later on. Can you guess what this is going to represent? Vector A over the magnitude of vector A. Maybe we'll write it like this. 1 over magnitude of A times our vector A1, A2, A3. What does this give us? This is going to give us the unit vector in the direction of A. And by unit vector, that means it has a magnitude or distance of 1. So we had a vector out here, and it went from here to here. This is in three-dimensional space, and I wanted the vector in the same direction, but with a magnitude of 1. Then that would be this expression right here. So now, what does it mean if I say vector A is parallel to vector B? It does not mean that they do not intersect, because if I have one here, it's a little hard to draw three-dimensional on this two-dimensional surface, and the other vector here went through, but let's say under it, then those certainly are not parallel, and they won't intersect. Again, this is assuming that this blue vector went under the white one, crossing through in three-dimensional space. So the correct definition of A being parallel to B is not that they do not intersect. So we say that A is parallel to B if vector A is equal to vector B times some scalar, and I'll use scalar m. So vector A equals m times B for some scalar m. Let's take a little look at vectors being parallel. So here's a vector. Let's call this vector A. Now another vector, I'll use a red color, will start at the same point and only go half the way. They look like they're overlapping, and so that's, let's say, vector B, and vector B is 1/2 of vector A. It's a scalar multiple of vector A. Perhaps another one, let's say I'll use like a blue color, will be twice A. So that vector, same direction, twice the magnitude, and let's say here vector C is 2 times vector A, again a scalar multiple. Let's consider a vector going in the opposite direction, so starting here and a vector coming down like this, and let's call that vector D, and perhaps vector D is, I'm not sure, maybe negative 1/3 of vector A, but still a scalar multiple. Now, it doesn't have to be graphically overlapping, so if I had a vector here call this vector u, and another vector that was over here. This sort of looks like the traditional parallel, and this is vector v. So these are also parallel vectors because one is a scalar multiple of the other. If we were to orient them both from the origin, then my u vector might look something like this, and then my v vector, which almost looks the same, slightly larger, like that. So they are also parallel. Now we look at the vector between point P and point Q, specifically the vector that goes from point P to point Q. And that vector, which we will call vector PQ, starting with P going to Q, is simply the difference in the corresponding components. So it would be x1 minus x0, and then the y would be y1 minus y0, and finally the same with the z. Next we look at the zero vector. The zero vector is just that. It's a zero with a vector, not to be confused with the number 0. The zero vector is simply the vector consisting of 0 for each of its components. The magnitude, obviously, of the zero vector is the number 0, the scalar 0. Now this is a definition that's required, and we say that the zero vector is parallel and orthogonal. Now orthogonal is a fancy way for saying perpendicular. So the zero vector is parallel and orthogonal to all vectors. That's similar to the definition that says 0 factorial equals 1. You can't really explain that 0 factorial equals 1, so mathematicians have defined it so we could use it in formula, etc. So the same is here. Zero vector is parallel and orthogonal to all vectors. So let's formally discuss this orthogonality. We say that vector A is perpendicular or orthogonal to vector B when theta equals pi over 2 radians, where we define theta to be the angle between the vectors, where theta is the angle between vectors, and we say that that is going to be between theta is between 0 and pi. So in other words, if I have two vectors here, this is vector A, this is vector B, there are two angles between them. There's the angle here, but then there's also the angle here. So we want the smaller of the angle for some uniform and standard. So we will say that two vectors are orthogonal when that angle between them is exactly pi over 2 radians.